Now we're getting into the thing where things are going to start getting confusing because we've done parametric differentiation. So that's where the x and the y are given in terms of t or theta, and you get a curve and you're interested in the slope of the tangent. And now we're looking at a different type of curve, which isn't the graph of function but something else. So the way this works is you get some equation in x and y, these variables equal to 0 or equal to a constant, say. Well, if there's a constant, you can take it away from both sides. So something like this. So an equation defines a curve in the plane. Now, in what sense? So this equation has loads of solutions, and what you do is you plot on the plane the solutions. So you get, this is a big idea, you get this link between algebra equations and geometry curves. So you have the solutions of the equation are points on the curve, and it works the other way around. Points on the curve are solutions of the equation. It's called the equation of the curve. Now you have met this before, and so here it says, oh, is a point on the plane. If it satisfies the equation, then it's on the curve. If it doesn't, it doesn't. So two examples are y equal to 2x plus 3. If you want to put it in that form, you can do 2x plus 3 minus y equal to 0. And the other one would be x squared plus y squared equal to minus 16 equal to 0. So two examples, y equal to 2x plus 3, which might look something like that. And suppose another one would be x squared plus y squared equals 16, which might look something like that. Okay, so all the points on this satisfy the x coordinate squared plus the y coordinate squared are equal to 16. And all the points on this satisfy that the y coordinate is equal to 2x plus the y coordinate is equal to twice the x coordinate plus 3. If a point, yeah, so this is how you get this relationship between equations, which is algebra, and geometry. So for example, if we look at, say, the point 5, 0, it doesn't satisfy the equation. So if you look at x squared plus y squared for that, you get x squared plus y squared, 5 squared plus 0 squared, 25 plus 0, 25 is 16. It doesn't satisfy the equation of the curve, so it's not on the curve. Whereas 4, 0, for example, satisfies the x coordinate squared plus the y coordinate squared is 16, so that is a point on the circle. And then say for the other one, point 0, 3, the y coordinate is equal to twice the x coordinate plus 3. And then you kind of get an interesting thing about these points, the intersections. So the intersection is a point, or points that satisfy both equations at the same time. Both equations simultaneously. And so algebraically simultaneous equations are finding intersections of curves. Okay, now what we're more interested in, although that's all very interesting, what we're interested in is are these curves smooth, and can we find the slope of the tangent to these curves? Okay, so here's a but. Now this one is a bit different because this is actually in 3 dimensions. So you can do this with 3 variables, and then when you plot the solutions, you get a 3D surface. So it's, if you can see here, so all the points, so for example, let's look at some points that are here. Not sure where, maybe down there somewhere, you have the point 0, 0, 0. Okay, and well, what might this be? It's very hard to say. I'd just be guessing really, but can we it'll be very hard to come up with a point actually, but some points that would work would be certainly 1, 0, 1. So the x coordinate to the 2 plus the y coordinate to the 5 is the z coordinate to the 9. Similar story, 0, 1, 1. Or we could talk about, say, 2, 2, so that'd be, oh, what's 2 to the power 5? Is it 32 or something? Oh, okay, so the left-hand side there would be 4 plus 32, and then it'd be the ninth root of 36. Look, we're getting a bit away. To be honest, I just wanted to put the picture of the butt. Right. So let's look at a particular example. So x squared plus y squared equal to 1. Now, if we plot this, let's see, like, why is this a circle? So, I'll probably just draw the circle and explain why it works. Okay, so take a point on, now this is a unit circle, so radius 1, so this is point 1, 0. This is the point 0, 1. This is the point minus 1, 0. And this is the point 0, minus 1. So, and the radius is 1. So what I'm just going to show that every point on the circle satisfies this equation. So if I take a point here, let's call it x0, y0, you can form a little Pythagoras situation, and you will get that, what are we going to get? Well, the square of the hypotenuse, well, the sum of the squares of the sides. So this side will be x0, this will be y0, so you get x0 squared plus y0 squared is equal to 1 squared. In other words, x0 squared plus y0 squared is equal to 1. So what you have is that every point on the circle satisfies the equation. Now there's a question about, is it possible that you have a point that satisfies the equation but it's not on the circle? So we will take a different point here, maybe x1, y1, that satisfies that the sum of the squares is equal to 1. So we'll do the same kind of a thing actually. Can I safely, yeah, I can still form a Pythagoras. So I'm just saying, is it possible that a point that's off the circle works? So this coordinate would be x1, this coordinate would be y1, and this here, well, let's see. So let's call this distance L. So we do Pythagoras here, we get sum of the squares must be equal to L1 squared, but, sorry, not L1, just L squared, but L is bigger than the radius of the circle. So L squared, so L is bigger than 1, and so this is strictly speaking bigger than 1. So therefore x1 squared plus y1 squared is not equal to 1. So a point outside the circle doesn't work, and similarly a point inside the circle doesn't work. So if you're talking about x squared plus y squared equal to 1, every point that satisfies that equation forms the circle, and every point on the circle satisfies the equation. Now, if we want to look at this in terms of tangents and stuff, what we have is actually two functions glued together, because the circle itself isn't the graph of function. So remember what a function is. It's number in, say x, number out, f of x. And if you plot the function, you're supposed to plot all the points of the form input, output. Now, if this circle was the graph of function, well, what does 0 go to? Because you've got 0 in, 1 out, and 0 minus 1 out, but it's supposed to only be in one number out. So this isn't the graph of function, but it's two functions glued together. The top, which is plus, I'm just going to write f1 here, because I write the formula down below, and the bottom. F2. So it's two functions glued together. And in theory, what you could do is you could differentiate, say if you want to know what's happening at 1 over root 3, so maybe for argument's sake, let's say that this is the point 1 over root 3, root 2 over 3, which if you look at it, sum of the squares is 1, it's on the circle. And you wanted to find the slope of the tangent there. So, well, what does the tangent look like? Something like that. You could differentiate f1 and substitute in x equal to 1 over root 3. But the problem is, not every one of these are called implicit curves, by the way. Not every implicit curve is so nice that, you know, you can get formulas for each little branch. So instead, there's a technique called implicit differentiation, which allows us just to differentiate away. Okay, so the way it works is similar to something that we saw previously. And basically it says that points on this curve y is a function of x. So see, you got a green bit here, it's a function of x. Now you don't have a formula for the function of x. Now with the circle you do, but in general you don't. But theoretically it is there. So the idea is, and this is called implicit differentiation, you write down the equation with the x's and the y's. You don't know what the y is, but you say y is a function of x and you just differentiate away. Okay, so for example, say you want to differentiate y squared. Well, you're differentiating the derivative of y squared. Now we're not going to write y squared, we're going to say, okay, implicitly, so say if you're near the point, the purple point, 1 over root 3, root 2 over 3, there is some that is on the graph of a function, a branch f1. So we have near that point that y is actually equal to a function of x near there. So say in this one where it's x squared plus y squared and you want to differentiate y squared, you say, oh, I'm actually going to differentiate y of x squared. And what we're going to do is we're going to get the slope of that, we're going to get the derivative of the branch, but it's going to be in terms of not just x, but x and y. I appreciate this is difficult. This is probably the hardest thing. Well, look, it's difficult. There's no two ways about it. So this is the chain rule. So the chain rule says you differentiate the outside function. Now, the outside function here is x squared. So you differentiate the outside, and the derivative of x squared is 2x. But the chain rule says you evaluate at the inside, and then you multiply by the derivative of what's inside. And the derivative of y of x, you don't actually know what y of x is, but you know you can say the derivative of it is dy dx. So what happens is you're going to have a curve, which I'll write down here. So some formula in x and y equal to 0. And if you differentiate both sides of the equation of the curve, you'll have x's, y's, and you'll also have dy's, dx's, so you'll be able to solve for dy dx in terms of x and y. So then if both sides are differentiated, you get an equation with x, y, and dy dx equal to 0, and you can solve for dy dx. And that will give the slope of the tangent to the curve at the point. Okay, so the derivative of y is just dy dx. The derivative of a function of y of x must be differentiated as a chain rule. So if you're differentiating some function of y, now we're gonna get into this habit of writing y as y of x to help us see these chain rules. So you're going to see that f is the outside function. So what does the chain rule say? Differentiate the outside, evaluate at the inside. Now you only write the y of x once, then you can just add that right y times the derivative of what's inside, and the derivative of dy dx is, or excuse me, of y is dy dx. Okay, so let's see some examples. So we got this cubic here, so there's a relationship between the coordinates on this curve. 3y squared is equal to x times x minus 1 all squared. There are two branches here, but we won't get into that. So let's do the implicit differentiation. So the first thing I recommend, and so this is just the theory. We won't, I won't push the theory. Well, it is okay. So if you look at the point x equal to 2 root 2 over 3, so this point, some part of the curve is a function. Now we can't actually say what it is here looking at this picture, but we just have to take a little bit of it. That much. So we're only interested in between those 2 points. That's certainly the graph of a function. So in this region, y is equal to y of x. Now we're not actually going to find out what it is, but I could do it here. Okay, so we rewrite the equation of the curve with, instead of y, y of x. So it's going to be 3y of x squared. Now the other reason is we're going to have in the next week, we're going to have differentiating with respect to x and differentiating with respect to y, and the derivative of y squared with respect to y is just going to be 2y, and it's going to be all kinds of confusing. That's why I really recommend writing this y of x. A lot of people don't actually do this, but this is my recommendation. Okay, so that's kind of that we're understanding that near this particular point, it's the graph, the bit on the curve is the graph of a function just near that point, and so there is some abstract function there, some form, well, it's not necessarily a formula, but it's a function y is a function of x. Okay, now we're going to differentiate both sides with respect to x. Now I'm just looking, we could, there's an option here of multiplying out the right hand side before differentiating. That does make the derivative on the right hand side a little bit easier, and I'll just show you how you do that. We won't do it though. So x minus 1 by x minus 1, if you carefully multiply it out, it would be x squared minus 2x plus 1, and then that's equal to x cubed minus 2x squared plus x, which is easier to differentiate than what we have there, but I'll just pretend we didn't see that. So we're going to differentiate both sides of this. I just need to write it down for a moment. So, well, we'll just write it up at the top here so we can see what we're differentiating. We're differentiating 3y of x squared equal to x times x minus 1 squared. Okay, so we're going to differentiate both sides with respect to x. So differentiating the left-hand side. So we're going to fix the 3. Now, what about y of x all squared? So you've got an inside function y of x and an outside function that's just x squared. So the chain rule says you differentiate the outside function. So the derivative of x squared is 2x. The chain rule says evaluate at the inside, which is y, and we only write y of x once, times the derivative of what's inside. And the derivative of y of x is dy dx. So that's the derivative of the left-hand side. The right-hand side is a bit easier to a degree. Now, you probably want to use the product rule if you don't notice that you can multiply it out. But when you're differentiating the second thing, you probably need a chain rule. Now, you can get away without the chain rule, but we'll do it here. There's no harm seeing lots of chain rule for practice anyway. So the product rule says when you've got two things multiplied together like this, the derivative is the first thing by the derivative of the second thing. So we're going to go with the chain rule here. So the outside function again is x squared. So the chain rule says you differentiate the outside, which is 2x. Then the chain rule says evaluate at the inside, which is x minus 1. And then the chain rule says you multiply by the derivative of what's inside. And the derivative of x is 1 and the derivative of minus 1 is 0. Possible overkill there, but no harm seeing more chain rules. That's the first thing by the derivative of the second thing, plus the second thing by the derivative of the first thing, and the derivative of x with respect to x is 1. Now, just in terms of the product rule, we'll show you what we did there. We did the first thing by the derivative of the second thing, plus the second thing by the derivative of the first thing. Okay, now our job now is to solve this for dy dx, so we'll just tidy it up a little bit. We've got 3 by 2y, that's 6y by dy dx. And let's tidy up what we got here. So how about, now the red thing is just equal to 1, so that doesn't really make any difference. So it's just 2x by x minus 1 plus x minus 1 squared. And maybe we should go back and read the question. First question is, use implicit differentiation. Yeah, so we find dy dx. We're nearly there. So we've got an equation now in x, y, and dy dx. And what we want to do is solve for dy dx. So all we have to do is divide both sides by 6y. So if we do that, we get dy dx is equal to 2x times x minus 1 plus x minus 1 squared divided by 6y. Okay, so that's the first part done. Second part. Hence find the equation of the tangent to the curve. So we'll just draw that using the picture, and we'll write some things that we expect to see. So the tangent to the curve here looks something like this. Now we recommend, or we think we're going to get some, so a line is y equal to mx plus c. Because it's going up, we're going to expect the m to be positive, and the c is where it cuts. We'll expect c to be somewhere around minus 1.5. So that's what we expect to see here. Okay, so so that's from the picture. Now, how do you find the equation of a tangent? Now, it's just a line, and you have a point, 2 root 2 over 3. You need a point and a slope. Now, the slope of the tangent all day long, we would have seen this last week, slope of tangent is equal to dy dx. And we have that. We just have to evaluate it at 2 root 2 over 3. So what have we got? So the equation of the line there is written like that. And how do we find m? So m is the derivative, and we want to evaluate the derivative at the point x equal to 2, y equal to root 2 over 3. So we're going to substitute in x equal to 2 and y equal to root 2 over 3 into that dy dx above. So we're going to have 2 times 2 times 2 minus 1 plus 2 minus 1 squared. That's substituting in the x, and then substituting in the y, 6 times root 2 over 3. And I'm just going to approximate this using a calculator for significant figures. We're hoping for about minus 1.5. So I get 2 by 2 is 4, by 1 is nothing, plus 1 over 6 by root 2 over 3. Sorry, we're not expecting this to be minus 1.5. We're expecting this to be, the slope to be positive. And it comes out approximately 1.021. So now let's use the line formula above. So y minus the y coordinate is root 2 over 3 equal to the m, which is approximately 1.021. If you want to use like the third form, the 5 root 6 over 12, that's great. Times x minus, what is the x coordinate is 2. So what we should do here, get it in the form y equal to mx plus c, multiply out the right hand side, and then add the root 2 over 3 to both sides. So get 1.021x minus 1.04 2. Now okay, we'll just keep going there. And so we'll add that square root to both sides. So we end up with y is equal to 1.021x. And so minus, sorry, this, no, I knew I did something stupid there. This should be 2.042. So I have minus 2.042, and I'm adding square root of 2/3 to both sides. So I'm getting minus 1.2255, which rounds to 6. So I'm not quite minus 1.5, but not far off either. So I've drawn it a bit too steep. It should come down. Yeah, you can see, if you zoom in, you can see it's not. It should be hitting more, if you do it correctly, around here. I'm just going to draw it and then get rid of it, something like that. I could try that a few times. Could be at it all day, I suppose. One more go. No. Give up. You might be able to draw with a ruler. I can't really use a ruler on the screen here. Okay, so we're going to do some more examples. I think we'll leave this video here. It's probably long enough on a break.